Perfect. Okay, so we are ready. So welcome everyone to our PDE seminar. Today we have the pleasure of receiving, I will attempt to pronounce it, Khawla from University of Lyon. And she's going to talk about the preliminary depth integrated model for tsunami propagation, including water compressibility and seafloor elasticity. So thank you very much for your participation and welcome to virtually to Chile.
Thank you so much for your introduction, and thanks for the invitation also, and to Khenya. And you know, it's a pleasure for me to be in a virtual meeting with you. It's my first time in South America virtually, so it's thrilling somehow. So today I'm going to discuss the work that I have been doing in my last 2 years in my postdoc. And actually, it's a collaboration between Gaël Richard and Arnaud Durand and me. And basically, this work is concerned with having a new approach to derive some kind of model to have accurate results with respect to time arrival estimations of tsunamis. So what I mean by this is that we are going to develop a kind of dispersive posedness type model. We already have accuracy of estimating time arrival predictions. So I will go later into details, and I hope I can cover all the aspects of the problem. So first, because I will present like kind of general background on deriving dispersive models, maybe, or models that are valid in the far from shore region, in particular for ocean waves. So first we start by linear shallow water equations. So people usually started by the simplest model possible because for far from shore regions, nonlinear terms are of negligible importance. So they said, okay, we will take the shallow water equations. And the shallow water equations actually, if I don't know if you have some background about what we mean by shallow water equations, but they are a type of equations that are derived from Navier-Stokes system by averaging the vertical depth velocity, and hence we have like a system of equations on the elevation of the water and the depth averaged velocity. And this new model, which is the linear shallow water equation, actually doesn't account for dispersion because we are including, because when we say dispersion, we are accounting for smaller participation and contribution of other factors in the fluid movement. And so in this frame of work, no dispersion is present, but we need dispersion for like ocean waves because they are so important. And that's why people started to look for alternatives when they are concerned with modeling ocean waves. So I may add here that at the level of linear shallow water equations that I will just like display here, incompressibility wasn't taken into account. We usually, when we hear about water waves modeling, incompressibility is always the ansatz to take. We rarely hear that compressibility of water is necessary, but as we will see later, it can contribute at the level of precision. So for linear shallow water equations, they didn't take into account incompressibility. The floor, the bathymetry or the topography, which is the floor beyond the ocean, is stationary. It doesn't move. It doesn't move. So so basically, what linear shallow water equations look like are the system in red. Maybe we can associate this with the graph below. So we have the ocean wave. Eta is the elevation. So first of all, H0 is the depth of the ocean at equilibrium, and then eta is the elevation from this equilibrium. U is the depth averaged velocity, as we all know, and G is the gravitational constant. So this is the linear shallow water equation that can give some insight on dispersive waves in ocean, but not so accurate results. In particular, we have discrepancies at many levels, at the amplitude level, at the velocity level, and of course, at the shape of the wave level. And then comes another type of dispersive models, which is the Boussinesq type equations. Of course, at the level of modeling, the Boussinesq type equations are like the second order of approximation from the linear shallow water equation. So when we have the Navier-Stokes system, we do rescaling, we do these stuff, which we have the first order. And when I say order, I mean between the aspect parameters that are very small. So we do something kind of Taylor expansion or asymptotic expansion in a way. And then we get first order. And for the first order models from Navier-Stokes, we have the shallow water equations. And the second order approximations are the Boussinesq equations. And they are second order approximations because they contain some small contributions that account for the second order. And these contributions are basically the non-hydrostatic pressure. So the main difference between Boussinesq equations and shallow water equations is that Boussinesq equations contain the non-hydrostatic pressure, or when we define the pressure, we say that the pressure is actually equal to the hydrostatic plus non-hydrostatic pressure. Whereas in the linear shallow water equations, we only have the hydrostatic pressure. And thus, including this non-hydrostatic pressure leads to have, like we have difference from the result we get before. We have dispersive effects taken into account, which lead to the change in the amplitude of the wave and change in the shape of the wavefront. And here, change means that we are closer to reality than the previous model. So closer to experiment, closer to what we see than the one described by linear shallow water equations. And Boussinesq equations, the usual one, also accounted for incompressible assumption and perfectly rigid solid layer. So one type of very famous Boussinesq type equations is the Grignard system, which is present here in blue. So this system has been recently, like maybe in between 2008 and 2016, I guess. I'm not sure about the numbers, but it has been rigorously proved to have solution. So this is the system in its simplest form, but then you can reformulate the system in order to have an operator in front of DTU here. But in its more simpler form, this is the structure of the Grignard system. And we see that the difference between this system in blue and the system in red. In particular, we have this additional term here. And this additional term, numerically at least speaking, is a bad term because, so if we define the dot, you see, so here I define a dot of the quantity to be the total time derivative, which means the materialistic time derivative, which is equal to, of a quantity x, it's equal to dtx plus u dot grad x. So, so double dot means I have twice capital T by dt. So, in sum, we have like an operator, which is elliptic operator here. And this costs a huge, this has a huge cost at the numerical resolution. And also, it wasn't that easy to solve the system at the mathematical resolution as well. So this is not the, if I want to say, the perfectly friendly kind of systems that you want to study for ocean waves. And although it has like included dispersive effects, and there is like very, I want to say, very accurate and good models for Boussinesq type equations, and also like extended Grignard systems, which actually give very good results. But if we want just to tackle the issue of accuracy at the level of arrival of tsunami waves, this system doesn't give like the most precision possible. And maybe I had to mention here that yeah, maybe I should have mentioned this earlier, but like all the goal of this work is to have, as I said, more accurate time arrival predictions, because the experiments and the incidents that happened have shown that the models that we have, even the most sophisticated models like have approximately 30 minutes delay sometimes between the model and reality. Like, okay, we say that there is a seismic wave, which, or maybe we just have in our like centers data that there is a tsunami, and our models expect that the tsunami to arrive, for example, now, and then it arrives after 30 minutes, which means that there is discrepancy to be tackled and studied at this level. And that's what enhanced all this work at the mathematical level. Because of course we based our study on physical and experimental studies that have been done in order to say that yes, the models need more information to have more accurate result. So that's here I come to talk about our contribution to the problem, because so here I just put that the Boyce's equation contains dispersive effects. And then I want to talk about the new model that we derived, but in 2 steps. So the first step was the work done by Gaël Richard in the reference one here in 2021, where he derived a Boyce's type model, which is compressible type model for ocean waves, or in particular for tsunamis. And this model in particular contained the non-hydrostatic contribution. And then this accounted for somehow the weak compressibility of the system. So if we want to sum up, if we want to just state the difference from the Boyce's equations, he changed the second assumption here to say that now I want to account for compressibility of the water. And by doing so, actually, he proved that his model, so finally he had like 4 equation model that I will display later, but just to give like a general insight, his model with this addition of the compressibility assumption has proven to have a decrease in the velocity from previous models, from the general Boyce's equations. And this means that weak compressibility actually accounts somehow or contributes to this delay that happens at the level of the tsunami arrival to the shore. And our contribution to the work, so this started when I started my first postdoc, it was to add the physical phenomena of viscoelasticity to the model that he derived, to the technique that he derived, in order to account, in addition to the weak compressibility, in order to account to the viscoelasticity of the solid layer. So what we mean here is that we have a huge mass of liquid that arrives when the tsunami wave occurs, when there is an explosion or the shift in the platinums of the earth, etc. So this huge mass will cause a pressure on from the water column to the ground. And this pressure causes the ground to compress a little bit in a manner similar to, in a behavior similar to a spring. And after the passage of the wave, the ground retains its initial position. And this thing is called the elasticity of the earth. So, and once we say that I don't have like a board to draw some picture just to show that, but you can imagine it that when the wave arrives and the ground goes down a little bit, then this means that you are slowing the wave from arriving to the motion or from continuing to flow. Show after derivation that it will account and contribute to the decrease in the velocity. But actually, when we did that, we also noticed that the viscoelasticity has contributed to other factors, which are the reverse dispersion and the negative, and eventually the negative peak, and as I said, accurate arrival time estimations. So including elasticity has revealed a phenomenon which was not noticed by previous models, whatever models they are, which is the negative peak that just precedes the main wave hump of the tsunami. And this was only noticed in experiment and by reality. And so yeah, I will start like by this was just like a general map on the motivation of the work and general framework of deriving ocean wave models for ocean waves or tsunamis. And then I will just show you it is a kind of quite good result, which is like informal limits between the model that derived by the guy here in one. So here I'm just showing you the work that was already done by him, in which he derived a four equation model just to account for compressibility of the water. So here's the Posedness, the Serigny-Nagdi model that I showed before. And here we have W being the depth averaged vertical speed. This vertical speed usually for shallow water or Posedness equations is either taken into asymptotics or either not neglected because it's usually considered very small with respect to capital U, which is the depth averaged horizontal speed. We have P capital B here being the non-hydrostatic pressure, and A actually is a constant which is equivalent to the sound speed. So the acoustic speed. This is the model that was derived by Gaël Richard, and actually we can prove that this model in the incompressible limit, that is when A converges to infinity, we can prove that this model converges to Serigny-Nagdi model, at least for informally, like formally speaking, naively speaking. But the issue is that this model was derived, it's true that this model was derived merely from physical basis. It's not like just pretending that there is some variable W or P. I would like to insist on the idea that this model has been derived from physical basis, but also it has been proven, like we will show now, that this model is actually a relaxation somehow to the Posedness equation, and in particular relaxation to this term that was like causing some complications. So if we rewrite this system here, just like we rewrite it in like reformulate it just for simplicity, we notice that we have in the second equation, we have a squared p inside the derivative, space derivative. And if we couple those two equations together, the third and the fourth equation, so here we have a squared p in the fourth equation, we can write a squared p in terms of w and then substitute w from the third equation. And eventually we can write this relation here between a squared p, d squared p over dt squared, etc. So we already know from the fourth equation that p tilde is of order a minus 2. So we have a squared p being being equal to three terms, the first two of which are of order a minus 2, and the third one here is actually equal to h dot dot, because h dxu from the first equation, which is the mass conservation, is equal to h dot, which is d capital D by dt of h. And then we will have like 2d by dt of h, and also we can neglect the order a minus 2 terms, a to power minus 2 terms. So eventually at the limit of a at infinity, we can write p tilde, sorry, here. So yeah, a square p tilde, not a p tilde. A square p tilde is equal to minus h squared over 3 h dot dot. So if we substitute now a squared p here by minus h squared h dot dot over 3 in the second equation, we obtain again the Serigny-Nagdi model. And this is how we formally at least prove that, okay, this is kind of a relaxation of the Serigny-Nagdi model, and we expect to have common properties in between. So, so for our contribution of the work, at least the work I did, we will take the same system of equations for the liquid layer. Of course, we will derive it from the beginning because we will have now boundary conditions to take into account, because we will consider the movement of the bottom. But as when it comes to the liquid layer, we will be dealing with the same system as here. So the same strategy he already derived for just accounting for compressibility. And then the next part would be to model the movement in the elastic layer and couple that with the, because we want to account for both compressibility now and viscoelasticity. Okay, we have the model. Model. So for modeling the solid part, so of course we rely all our assumptions and that's on experimental physical papers and results which are like elite. And so these experiments have shown that only, so you see that the Earth beyond the wave, or maybe the solid layer beyond below the ocean layer has many different structures, but the experiments have shown that only the mantle, in particular the crust and the upper mantle, undergo deformation. Even in the mantle, there exists an age at which beneath this age there is no deformation exists, and this is because at this capital H we will have a sharp increase in density. And once we have sharp increase in density, we expect that, okay, there is no passage of information by the wave, and thus there is no like effect of this elasticity on the rest of the part of the solid. So we ended up on using, because we don't want to, we want to account for this small displacement, if you want to say, but we don't want to complicate our model. So we ended up using the Kelvin-Voigt model, which is a simple model describing the evolution of the total stress tensor in the solid and the displacement or the velocity in the solid, the evolution of the evolution of the velocity in the solid. So here we have, yes, and the first equation is the evolution in terms of the elastic stress. So for the elastic stress, we have the governing equation is taken by Hooke's law. And for the viscous stress, we have the usual viscous stress taken for, well, this is not as, there's analogy between viscosity in solids and viscosity in liquid, but it's the usual state equation that we take. So we have here mu and lambda being Lambda's coefficient, which are related to Hooke's law and elasticity. And the viscous stress tensor, we have mu prime and eta prime being the viscosities. And here we have that the velocity is related to the total stress, which is the sum of the viscous and elastic stress. So the next step that we expect is to average across the depth of the solid layer, as we did for the liquid layer. So we use scaling, and for scaling we have some experiments which gave us some insights on the sizes of different variables and different components of the variables in the solid layer, and thus we were able to use the smallness assumption that we used in the liquid part to use this parameter in order to rescale the ones in the solid part. So epsilon, usually it's the smallness or aspect ratio in the solid part, sorry, in the liquid part, but we were able, due to some data, to evaluate the sizes of the components of the variables we have with respect to this epsilon. And then we ended up in this approximation of the system. So instead of the total system, we have neglected all order epsilon terms, and thus we neglected the normal component of velocity, and we just have the vertical component. And also we neglected the horizontal component of velocity. We only have the vertical, and we also neglected the normal component of stress, shear stress. We only have the shear stress, and we neglected the normal component. And then we expect to, as I said, to integrate over the depth of the solid layer. And we define, so this is just technicality. I had to put it somehow, just not to suddenly put this system in front of you, but like this is really technical. We just define Q being the average depth vertical, this velocity in the solid, and S being the average depth shear stress in the solid. And by closing the system, we finally have this these two equations here. And we will later see that these two equations are coupled with the liquid layer via the term at the here. And also B will have some contribution to boundary, B being the bathymetry. So it will be the topography. So as you see that this system has kind of parabolic behavior due to the presence of dxxq, which is due to diffusion viscosity due to taking into account the viscosity in the solid layer. So what we did, so this is not so good for numerical implementation later on, but what we did is that we carried on all the results that you will see later with this term, and it was clear to us even at very precision values that this term doesn't contribute to the accuracy of estimations. So we can neglect this term because eventually this term only accounts for the propagation of the elastic wave, just transverse elastic wave, just in the solid layer. So the information liquid layers. So this is really, it's not an important for as long as we are concerned just from the information that we take from the liquid layer, from the wave, water wave. So the final coupled system is this one. So the first equation actually comes from the boundary conditions. So it's like there is some asymptotic play here in order to place this this condition. And then we see that the second and the third equations are actually the equations that come from the displacement in the solid averaged. And the rest four equations are the liquid layer that I presented at first, that the one that was derived by Gayad Richard. And you will see here that it's a little bit of discrepancies between the liquid model here and the one before. Like you will see some R here, some Q0, Q1. It's actually, this is the full model where he accounted for compressibility. So R will be the average depth density. And Q0 and Q1 will be like some terms related to Mach number. But there is another version, simpler version of this system of equations, the one that I presented before. It's called the quasi-incompressible, where we just imagine that R is equal to 1. So just like to not have some confusion at the level, what's the terms here in R, Q0, Q1, they are just terms related to the compressibility. So now that we have the final coupled model, we will ask some questions concerning what about the mathematical structure? Is it good to study? What information can we take at the level of wave speed packets and dispersion relation? And finally, the numerical validation. What about how did this model and all this work and all this complication improve the results that we get from Gaussian equations usually? Like, did we account really for the accuracy at the level of time arrival estimations? And maybe there is a fourth point that I would like to address today is the well-posedness of the system, but just the liquid layer. So we haven't started integrating the solid layer yet, but we have some concrete results on well-posedness results, rigorous results for the liquid part. So as for the structure of the system, we have that the system is hyperbolic. We have 7, as you see, we have mainly we have 7 equations, so we expect 7 eigenvalues. Well, you will see that there is lambda1 equals 0. This is just because we take one boundary equation into the system. So maybe if we consider the 6th equation without the equation on dTB, by taking like P, some given or source term, we will get 6 equations. So this is not something bad. This is just accounting for the boundary condition in the first equation. The second and third eigenvalues, of course, we have the transport in the liquid, the transport in the water. So we will have U, and then we will have the waves corresponding, the eigenvalues or wave speed, the speeds corresponding to the acoustic wave, since we accounted for compressibility. So here where we have A, And then we have the 6 and 7 actually are the speeds of the transverse elastic wave, and these are the speeds that are only present in the solid part. So they come from the second and third equation. So it's pretty much comprehensible and informative what we got from the eigenvalues. And now what we have to do is to ask for the energy. Does my system preserve energy or conserve or give dissipative energy maybe? So what about the energy? The energy, so actually, since we have like contribution from the solid part and contribution from the liquid part, we would expect to have different ranges of energies. It's not that just the usual, total energy, kinetic and potential. So after deriving the energy of the system, we found that we have dissipative energy if we include the viscosity, which of course adds some kind of diffusion and thus dissipation at the level of energy. So the viscosity in the solid part. And if we neglected viscosity, then we will have conservation of energy. We have here EL total being, maybe I can switch to the slide. So EL total will be the sum of kinetic, potential, and internal energy. Of course, internal energy is related to the non-hydrostatic pressure here. We have the elastic potential energy, which is similar to the one we get from Hooke's law for elasticity. And we have the energy related to the transverse elastic wave. We have the strain and the kinetic energy described by the Q square and S square, the average depth, velocity, and strain. This is at the level of the energy. And then we derive the dispersion relation of the equation because we are more concerned by the linear behavior or non-linear behavior just by dispersion because we want to see the impact of the different wave packets and what that includes and induces on the result. So as you will see, this is a cumbersome dispersion relation. It's of order 6 because we have here omega 4 and here multiplied by omega squared. So this is an order 6. This means that we will have solutions. So omega 6 equal function of the wave number, and then we will expect that we will have 3 branches of solutions. And this is theoretically expected because we know that we accounted for the hydraulic branch, the gravity branch. We have elastic branch due to elasticity in the earth. And also we have the acoustic branch, which is due to the compressibility of water. So the graph of course, we can't solve this equation analytically. What we had to do is just resolve it numerically, and we get the following result. We have in black is the acoustic branch, in red we have the elastic branch, and in blue we have the gravity branch. So there's a lot to discuss on this graph, but mainly we'll be now concerned with the information and in particular in the speed of the gravity branch, just to validate our results at just the first step. So yeah, but just before talking about the velocity, the wave speed, actually this dispersion relation, this slide is like kind of validation of the dispersion relation that we got, because it contains the 3 aspects: compressibility, elasticity, and the usual hydraulic one, the gravity branch, gravity contribution. So if we don't take into account, for example, elasticity, that is, we are just accounting for compressibility, then we recover from this equation in the box, we recover the dispersion relation that was already derived by the model that only contains compressibility by Richard in 2021. And then from this, if we neglect weak compressibility, then we recover the one that was obtained for a Grignard system. And this shows how we have like 3 levels of relaxation between compressibility and elasticity and the gravitational surface wave. And of course, when I say neglect compressibility, this means that, so compressibility here, okay, so maybe this is technical, just like you take some constants here equal to 0 or equal to 1, because they are related to the density, to average density. And then we plot the phase speed and the phase speed just for the gravitational branch, of course. And here we notice the new phenomena that's new to the literature. And so actually in red, in black, you have the phase speed that we got from the airy theory, which is the linear, like perfect condition theory of water waves. In blue, we have the phase speed that comes from just the compressible system, so just the 4 equations. And then in red, orange, and green, we have the new coupled, like very long system, but for different values of h. And here I recall that h actually is the depth that we take in the solid layer. It's not the one that in the liquid layer, it's the depth that we take in the solid layer. So as you notice, first of all, compressibility in its turn proves that it can decrease the the phase speed by like a certain amount, certain percentage from the linear one. So this is already an enhancement at the level of including compressibility. And then once we include both compressibility and elasticity, we notice that there is another contribution to decrease the phase speed. And this is the whole goal of making this work. We want to account for more precise velocity fields estimations or calculations, and thus this means that more precise time arrivals. But there's another phenomena that we notice here, especially in the orange and red curves. You notice that usually it's monotone. The behavior between phase speed and wave number is monotone. But for the orange and red curves, we notice that for small range of wave number, we have an increase in the phase speed until like a certain value of wave number, after which it retains its monotone decrease. And actually, this is the effect that we notice in reality, but it's not captured in the systems, which is called the negative peak. So when they see, like naively speaking, when they see the tsunami coming, there is always like a negative peak, which means like a negative wave, which precedes the main wave hump. And this negative peak is not included or not noticed by models. So when you have like your numerical simulation or your data, you can't notice that. And actually, by including elasticity, we could recover this negative peak, which eventually leads to negative dispersion and causes this behavior between phase speed and wave number. And the good thing here is that we had like different behaviors for different values of h. So we couldn't have this result for h, for example, equal 100 kilometer, but once we increased h, we had more quantitatively of this dispersion, like its amplitude, its speed, its like contribution to dispersion relation. We may need to have like more than solid layer in order to couple them with a liquid layer and eventually have more quantitative results. So this is a work we haven't done yet, but it was like the first observation or the first note that we put down once we got this result. And then I will speak about how we ended up implementing our model at the numerical level. So basically, we have a very beautiful structure for the hyperbolic system. And usually we use finite volume with Reznov-Raman solver for that, which is like not very costly and can give results in the most easiest way possible. But here since we have like different wave packets, we will be using a splitting method in which we treat each contribution of the system that is corresponding to a different velocity separately. So first of all, we will have the gravity part. The gravity part is the usual part that just contains, like, it's a very how to say that? It's a very put out system that just contain, like, the main velocity here is the gravitational velocity. The contribution to from gravity to the hydraulic velocity, and then we set up the transport of W and P to zero. So we don't notice here the elastic wave, elastic speeds, and we don't notice because elastic speeds will appear here in the viscoelastic part, and the acoustic speed will appear here in the fast acoustic part. So for that, we treat the slow part explicitly. The kind of slow fast, which is a part which is corresponding to the viscoelastic contribution, we treat it also explicitly, but with different interface speed in the Riemann solver, because we have a large speed here. And finally, the fast acoustic part, we treat it implicitly. So this is called splitting method. Also, it's called the Emacs scheme. Implicit explicit scheme, and this has been used a lot in the framework where you have a model with different wave packets that are really like not very close to each other. So as for the gravity part, so as I said, we used hyperbolic part. For the hyperbolic part, we used finite volume method. There is some source term here that was treated as central finite difference. And this is just like optimization technique. It could have been here, but just for optimization and for the sake of energy that I will not discuss here because it's another whole issue. And also for the Riemann solver here, we use the hydraulic eigenvalues because the speed, the greatest speed here, like the highest value speed is the one from the hydraulic part, from the gravitational part. And then for the viscoelastic part, we also use the explicit method, finite volume. There is some terms here. So if we include viscosity, as we see here, we will have central finite difference for the terms on that are treated as source terms. And we will have, like, because we have quite a high range of velocity, which is the velocity of the elastic wave, then we will have in the interface speed of the Riemann solver, we will include this. This is just to include that we don't have blow up afterwards. And as for the fast acoustic part, we will be treating this implicitly in order to account for the phenomena that is conveyed in this part. So it's difficult to have acoustic wave and treat that explicitly. It will cost a lot at the level of CFL. So the best method, which is already like used method, which is the Emacs scheme, says that your highest speed value should be treated as an implicit method. For that, we use the backward Euler method, the classical one. Everything considered on the right of equation considered as source terms that are discretized as in a central finite difference method. And finally, this is kind of semi-implicit, but also this is just technical. It's not like totally implicit due to the relation here between W and P. So like you can actually, when you have this in implicitly, you can bring P from the first equation and then you can join them, and it's kind of semi-implicit. And then we have finally this, sorry, but can someone tell me if I'm like ahead of time or something?
You still have a little more, 5 minutes, I guess.
Okay, so I will just describe this fastly. I think I'm good. So this is, we run a solitary wave, of course, to validate the model. We use TFL condition equal to 0.8. And we noticed here that, so of course we have these colors. So we have the blue I mentioned today is the one in, and it's the first one to arrive, as you mentioned. So this is why it was numerically expected to arrive before the actual wave. And then once we include compressibility only, which is the one in blue, we notice that there is a delay from the black to the blue. So this is the front of the wave, and we notice that the blue one arrives later than the black one. And then we included the elasticity, which is the one in red. And also we noticed more delay. And of course, we included elasticity without compressibility just for comparison, and we have the one in green. So what I want to mention here is that in addition to the time delay and having, of course, we have quantitative measurement of these discrepancies, and if it accounts for the real difference between previous models and reality, and it does to a like 90% accuracy. And second, I would like to mention here just at the level of elasticity, because the models that include elasticity are the red and the green one. So for the red and the green one, you can notice here that the wave goes beneath zero level. And this is the negative peak that I was talking about. So this negative peak is only noticed when there is elasticity, and not noticed even if we include other factors as compressibility. And of course, I would like here to stress again that also including elasticity will deform or distort the wave shape, and also like including elasticity due to this negative dispersion. So you will have like lower peak from the front, and you will expect like you will have higher oscillations in the tail at the back. So that's why we see here that due to dispersion, we have higher oscillations in the back. So this is a very great validation of the model. We have really like checked visually the things that we wanted to account for. And so yeah, I will just like mention, because I'm a little bit out of time. I'll just mention that our recent contribution to the work was to take the model just in the liquid part, neglecting elasticity at the moment. Well, in the work, we are including bathymetry, but here in the presentation, I will neglect bathymetry, just not have like cumbersome system of equations. And we are collaborating with Vincent Duchesne from CNRS in order to prove well-posedness, classical solution, strong classical solution for the system. This system is kind of singular kind of systems, and there has been a lot of literature that I will not have time now to go over them, but we will be reformulating our system, because if you see here, the system in one is different from the ones I presented before, maybe at the level of terminology, like we have Q and kappa before we have P and W. This is just algebraic transformation in order to have like symmetric form at the end. And here we introduce two scales, delta, which is being the aspect ratio, and A is being a parameter equivalent to the inverse of Mach, and thus equivalent to the acoustic speed. So we will be tackling this kind of systems. So if you notice, we have different scales of parameters. We have A delta, we have A, and we have, yes, so basically delta is somewhere, but it's hidden. Yes, delta appears because of the bathymetry, but I didn't include that here. So basically, we will just be dealing with A delta and A. But if we included bathymetry in addition, we will expect to have delta in front of some of the terms. So you see we have three ranges of parameters. So A delta is in some range, in the middle range. We have A very big, and delta, or maybe delta inverse. So there is like competition or comparison between these scales. And this makes it difficult to prove, like to use classical methods in order to prove well-posedness of such systems. So naively speaking, we will be dealing with a vectorial form system. It's easier than taking this huge one. So U will be linear combination of eta, U, P, and W. This is the factor that you saw before. So U basically, okay, so maybe it's not U, it's V, but yeah, you can understand what I mean. So V will be like H, small u, Q, and kappa, and then we can reformulate the system in the following form. So here we have DTU and multiplied by matrix, which is symmetric positive definite. We have SIU also, it's symmetric, it's multiplied by nabla U or grad U, and we have the first matrix, which is, so L1 here is skew symmetric, and it's it's multiplied by A, and we have another part, which, so the L matrices, the skew-symmetric one doesn't contain derivatives, whereas the symmetric one contains derivatives. So, and we have delta in front of it. So as I mentioned here, we'll have contribution from bathymetry, but since I didn't include bathymetry here, you will not see it. And then we say, okay, I have a general form of system, which is hyperbolic. There is a lot of results in the literature. Let me see how I can prove classical solution of such kind of systems. And actually, we have some difficulty treating this because, as I mentioned, we have different regimes. And this is called like three-scale singular limit balance law. And the energy approach to prove classical solution. And in particular, if you want to see this, so this is a graph we had from the numerical spectral method simulations, not the numerical one, of the variable P, which is the non-hydrostatic pressure. And you can notice here that how small is already the scale. And even in this scale, you notice that there is these oscillations. And so usually if I don't have these oscillations, I would just have like a curve going smoothly down and then going up and continue. But since I have these oscillations and they are of order very small, this means that I'm having generation of new scales. And this generation of new scales is due to the presence of delta A delta and A. So this is why the classical methods don't work. So there is some literature, some pieces of papers there in the literature that already tackles this kind of systems. We have here Stephen Chauchet. It's work since 1986, and it's very important work where he used the method of, okay, I can't prove functional energy in the usual Sobolev norm. Let me introduce a new norm to my Sobolev topology in order this norm to be equivalent to the one like the classical one, and this norm would allow me to balance the energy estimates. And this new norm actually is defined here. Well, in the paper of Chauchet, he only used mutations in the scale regimes in time. But then Vincent Duchesne, which was the person we are collaborating with now, in 2019, he proved the method for two scales, for time and space scale generations. And the norm that he took into account is somehow similar to this norm. So this is the norm that we are using now, but he started like the analogy since then. So we have preparation of the size of our solution up to some order in time, which we will call M. And after this time, we have that solution will blow and will generate like some oscillations. And thus we can add this second part of the norm in which we multiply by some weight, which is very small weight, in order to account for these oscillations. So this is the kind of norm that allows to use some new strategies, new functional energy strategies to prove well-posedness of the previous system. Yes, and finally, I would just like, so these are some references from the physical papers that we based our study, our derivation for both like the elastic and the compressible part on. So if anyone would like just to take notes of references, this would be like helpful. And that's my talk. Thank you for listening. I'm sorry also for taking a lot of time.
Well, thank you very much for your great presentation. I open the space now for questions in the audience first.
Good morning. Can you hear me?
Good morning. Yeah.
I have a question. It's about can you come back to slide 21?
Yep. Yes.
Yes. If you increase the depth of in the system, what in the elastic case, what happens into the relation between the wave and the negative speak?
Yes, so actually our validation is all qualitative, not quantitative. So I can't give like a percentage of relation or kind of relation between how much, but what we notice is as much as we increased the depth of the solid layer, we will have more information from the bottom on how the bottom is deforming. Although they are very small contributions, but you will notice the negative peak more when you increase H. But this is not quantitative because we haven't like launched the initiative to have quantitative, number-wise and size-wise study on the relation between H and the negative peak. We just noticed here that we did like several tests, and once we increase, because this cut of the monotonicity of the behavior between the speed, velocity, and wave number is also an indication of the negative peak. So here we notice that if we increased H, like 410, we notice more the effect of negative dispersion. So I could say that you can see it more, but it's not quantitative. Our work was only just to validate the model. We saw the phenomenon, and we didn't tackle that like thorough quantitative result on this, because this work has opened a lot of doors for us. So this is one of the possibilities that we are thinking about, and also like including two layers in which you couple the first solid layer with the second one. So you are, when I say two layers, this means two different densities and thus two different speeds. So there is a difference between the speeds in the first solid layer from the speed in the second solid layer, and thus you will have different propagation of information, and eventually you will have some more quantitative result at the level of dispersion, negative dispersion. So this negative peak.
Thank you.
Hello, Claudio. So I have just a question, very naive, but it's on the part that you call it the elastic part, right? When you model the Earth itself. Yeah. So my question is related with the fact that you have plate tectonics usually. I mean, how do you simulate the origin of a tsunami? With the initial conditions, or?
Yes, actually, we don't take we don't take the modeling from the original source of tsunami. We just follow from the moment where there is. So you will start by certain. Actually, what couples all the system is the deformation and the bathymetry. So what we will do is that after some distance from the origin, because it's not origin-wise related, you will take data. So you will start by bathymetry moving downward, creating elastic wave. You see that you model the propagation of this elastic wave, and you couple it with the wave, tsunami wave propagating in the fluid part. So actually, you take your data from like some distribution, if you want to say, distribution of the bathymetry, and then making it vary in time. And this is what we mean by elasticity, actually. Like, this is naively speaking, okay? So making the bathymetry move in time due to the propagation of tsunami, and then you work on the boundary. Of course, this whole happens on the boundary condition between the solid and the liquid part. So you take your data, initial data from there. You start from some configuration of bathymetry, you make it change. So the bathymetry DT change in time and in space. And this is what creates the wave, like it creates this stress, the compression in the solid part, and makes a transverse elastic wave, propagates in the solid part and transfers some information to the wave part, and then it propagates some information to the liquid part.
Okay.
I don't know if I answered your question, but this is at the level of like initial how we start our modeling and our system.
Okay. And a second question that I had in mind was with respect when you compute the engine values of the hyperbolic system. So my question is related with the fact that you are saying essentially that your system is of hyperbolic type. Maybe I'm wrong, but that means that it may be possible to have shock waves or, I don't know, any other type of solutions that are not usually related to
No, we don't have shock waves.
No, they don't have.
No, don't have shock waves. No.
Okay. Okay.
Yeah, we don't study shock waves for tsunamis, at least for ocean waves.
Okay, great.
Yeah.
Thank you.
Welcome.
Any other questions here? Okay.
Axel, one question: in the arrival time is larger or smaller for your model in page 21?
Yes.
It's larger, no?
No, actually, this is the front of the wave, so you can see.
It's smaller.
Yes, this is the front. It's smaller. So it arrives at later time. You see.
Yeah.
Yeah. So my wave arrives later. Like imagine they started at the same time. The first one to arrive is the black one, and then the blue one, and then the green one, and then the red one.
So it arrives later, no?
Yes, it arrives later.
Yeah. And this is due to the absorption of energy.
Yes.
In the soil. So my
energy.
question with respect to the model in page 10, no, the same as before, was do you think that there's a way to simplify even more the model, trying to just to recover this arrival time prediction?
Well, you can try linearizing, of course.
Yeah.
Because for tsunami waves, you are speaking for systems which are far from the shore, and then you have nonlinearity is negligible due to the shallowness parameter, and then you can linearize. I think we ran we ran some tests on the linearized. So they give you qualitative, not quantitative. But like simplifying, what I want to say here that this is what I stressed on the beginning, is that we are really dealing with like 0.1, like not 0.1, 1%, 0.5, 1.2 precision. Yeah. So even the terms that you want to neglect or simplify in order to have simpler result will not show this precision. You know, like even compressibility of the water, everyone knows that no one accounts for compressibility. Most of the cases, they don't account for it in water waves, at least. So here we accounted for it, and it have shown that it has shown that no, it accounts for this delay, you know, because okay, so one of the incidents that happened is the Tohoku tsunami in 2011, in which there was like 30 minutes or maybe 20 minutes delay. I don't remember the number, but like it's a significant time for people to take for risk management and all this stuff. So we are really dealing here on the precision. Maybe for some models which doesn't account for tsunami, this is okay, you know, like it's okay. But this is just model to really have precise estimation. So anything we want to simplify, we will know that it will like retro pass and will not give good results.
Yeah, my question was 1D model, no? When you pass to 2D, for instance, you have to replace. It's more complicated. It's very important.
Yeah. This is 1D, of course. We also working on having 2D we started already like having some 2D formulation. And numerically speaking, we have some codes. We already have a team working on codes with Toulouse, which is in Toulouse. So we already have some information corresponding to the 2D simulations. At least I'm speaking on liquid part. So for the moment, we don't have any. So no, but the solid part numerically it can be included. It's well, yeah. I just confused. So we have some numerical codes that run for 2D. So we're not expecting to have problems. We have rigorous mode, like very accurate codes. So I don't, but yeah, maybe, but also like at the level of posedness, as I showed you, will be eventually dealing with a vectorial form. And we expected like the 2D to be something, it will be encoded here. It won't make any problem. So once you got the results for 1D, I don't think it would be problematic for 2D.
Okay. Also in the model 10, we could say that the elastic
page 10, yes.
The elastic part is a viscoelastic spring, no? Essentially.
It's the same equation as spring plus viscosity, which is eventually okay. So we needed viscosity like to have some diffusion in the model and etc. But in the code, but actually, if you just want to talk physically, there is no transfer of information to the lip because we are concerned only with the water wave, right? We don't care about the elastic wave propagating in the, as long as it doesn't have information shared with the water wave. We don't care about what propagates in the solid.
Yeah.
So this is just something that numerically can enhance a little bit because it will add some dissipation, but it doesn't contribute to the wood because for the part I did, I neglected always the viscosity in this. So you can say it's just a spring, elastic spring.
Okay, thank you.
Welcome.
Okay, are there any questions from our Zoom audience?
No, I think there aren't any questions.
No, I think no. So if there aren't any more questions, let's thank our speaker again for the very nice talk.
Thank you. Thank you for the invitation and for the presence today also.
Perfect. Thank you so much. It was a very, very nice talk.
Thank you. I'm sorry for like having a lot of time.
No, don't worry.
Thanks. Bye.
Bye-bye.
Bye-bye. Thank you.